Section 7.5, Solving Trigonometric Equations. In this section, we're going to focus on solving equations with trigonometric expressions in them. There are quite a few challenges that we come across when solving trigonometric equations, and we're going to discuss a few of those now. One thing that we're used to doing when we're solving equations is using inverse operations. So for example, if we look at the equation cosine theta equals 1/2, we have already defined an inverse operation of cosine, or an inverse function for cosine, and that is cosine inverse. If we thought about applying cosine inverse to both sides, we're conditioned to think that the cosines would cancel, and we'd be left with theta equals cosine inverse of 1/2, and cosine inverse of 1/2 is pi over 3. However, there's a problem with this method. For instance, they said find all of the solutions to the equation. Are there other solutions to this equation that we did not account for? If we check with the unit circle, we see at 5 pi over 3, the x-coordinate is 1/2. So cosine of 5 pi over 3 will equal 1/2. That means 5 pi over 3 should also be a solution. So issue number one with trigonometric equations is we can't necessarily solve them using inverse trig functions. Now, sometimes we are going to use inverse trig functions, which we'll discuss later, but if we can solve them without the inverse trig functions, it's actually a lot easier. So if we restart the problem, instead of thinking about inverse operations, and we just think cosine of what angle equals 1/2, we can at least use the unit circle and see two such angles are pi over 3 and 5 pi over 3, because the x-coordinates of those points will be 1/2. So here, I have two solutions. But are those the only two solutions? Well, if we just limit ourselves to the unit circle, yes. But remember, trigonometric functions are periodic, and this is because of coterminal angles. If we consider the 5 pi over 3, if I were to say subtract 2 pi from the 5 pi over 3, I have that cosine of negative pi over 3 also equals 1/2. So negative pi over 3 should also be a solution. Same thing goes if I add or subtract integer multiples of 2 pi to 5 pi over 3, or pi over 3. So my equation isn't just two solutions. It turns out I actually have infinitely many solutions. Every angle coterminal to pi over 3 will also be a solution. All coterminal angles differ by an integer multiple of 2 pi. So one family of solutions is pi over 3 plus 2 pi n, where the 2 pi n is accounting for the fact that I'm looking at all the possible coterminal angles of pi over 3. Same thing goes for the 5 pi over 3. Since 5 pi over 3 is a solution, then 5 pi over 3 plus 2 pi n is a family of solutions to cosine theta equals 1/2. So here, I don't just have two solutions, I have two families of solutions. Now the same thing can be applied when we discuss the equation sine theta equals 1/2. For sine theta equal 1/2, I want to find points on the unit circle that have a y value of 1/2. Those would be pi over 6 and 5 pi over 6. So two solutions would be pi over 6 and 5 pi over 6. But coterminal angles of pi over 6 and 5 pi over 6 will also be solutions. So just like before, I'm going to add 2 pi n, where n is an integer, in order to find a family of solutions. And these families would be all the angles coterminal pi over 6 and 5 pi over 6. And that would represent all of these solutions to my equation sine theta equals 1/2. As we've seen in the previous examples, trigonometric equations have multiple solutions. If we recall from our previous units, sine and cosine have a period of 2 pi, while tangent has a period of pi. Because of the periodic property, trigonometric equations will always have infinitely many solutions. In order to express all the possible solutions to a trigonometric equation, we're going to write a family of solutions by adding either 2 pi n or pi n, where n is an integer, to the solution to the equation. What makes solving trig functions so difficult is that there's a lot of different ways to write a trigonometric expression, as we've seen throughout this unit. So we're going to look at a couple guidelines and quite a few examples of different situations and how to handle them. The guidelines are the following. First, look for a pattern that suggests an algebraic property, such as a difference of squares, or look for opportunities to factor. You want to try using substitutions. Substituting trigonometric expressions for a single variable, such as x or u, can make the equation transform into something that's easier to understand, especially in the case of quadratic-like equations. Solve the equation the same way you would an algebraic equation, such as isolating trig functions, trying to factor, techniques like that. Substitute the trigonometric equation back in for the variable in the resulting equation. After you do solve for the variable of the substitution, you do want to replace your variable with your trigonometric expression to finish solving. Then you want to solve for the angle. One thing to note, identities may be needed in order to help simplify an equation, or even to rewrite it into something that's easy to solve. So as I stated earlier, there is no one set way on how to solve a trigonometric equation, but we are going to look at a few different scenarios and how to handle them when we see them. Now we're going to solve the following equations. Notice that in each of the three equations we see, there is only a single trigonometric function. When we only see a single trigonometric function, our goal to try to solve them is to first isolate the trigonometric function, then figure out all the possible inputs based on the equation. So for example, if we were to solve 2 cosine theta minus 3 equals negative 5, first we should try to isolate cosine. So first, we'll add 3 to both sides, then divide both sides by 2. Now we need to figure out what angles cause cosine theta to equal negative 1. If we go to the unit circle, there's only one such value. That would be pi, which is associated with the point negative 1, 0. Since we're trying to solve the equation, that means we want all the solutions. So pi is not enough. There are more solutions because there's infinitely many angles coterminal to pi. So to represent all the possible solutions, we're going to add 2 pi n. So all of our solutions to 2 cosine theta minus 3 equals negative 5 is pi plus 2 pi n, where n is an integer. Now we're going to solve tangent of theta minus pi over 2 equals 1. Notice in this equation, our input to the tangent function is theta minus pi over 2. And here, our trig function is already isolated. So what we want to do is figure out all the possible values of theta minus pi over 2, which is the input to tangent, that will cause our tangent to equal 1. If we look at the unit circle, we do see 2 values. However, thanks to the periodic property of tangent, specifically that is a period of pi, we actually only need one solution, because our 2 solutions from the unit circle, which would be pi over 4 and 5 pi over 4, differ by pi, 1 period of tangent. So we only need a single family for tangent, and we have that theta minus pi over 2 equals pi over 4 plus pi n. But keep in mind, this is only the value of theta minus pi over 2. We still need to solve for theta. To solve for theta, you would have to add pi over 2 to both sides. And when we do, pi over 4 plus pi over 2 would be 3 pi over 4. So theta would equal 3 pi over 4 plus pi n. Typically for sine and cosine, we will get 2 answers or 2 families of solutions, except for in the case where sine or cosine equal 1 or negative 1. Because they're the extremes of the unit circle, that is the case where we only get 1 family of solutions. With tangent, because its period is pi, we're only ever going to get 1 family of solutions. Next, we're going to solve 2 sine squared of 2 theta minus pi over 2 minus 1. Just like our previous 2 problems, we only have the single trig function of sine. So the first thing we should do is isolate sine. We'll start by adding 1 to both sides of our equation. Then we'll divide both sides by 2. Next, to get rid of the square, we'll square root both sides. And since we're square rooting both sides, we can square root the numerator and denominator separately, and also remember the plus or minus. So now we have sine of 2 theta minus pi over 2 equals plus or minus 1 over the square root of 2, or sine of 2 theta minus pi over 2 equals plus or minus root 2 over 2. Now we need to figure out all the possible values of 2 theta minus pi over 2. Since we're dealing with plus or minus, we should split this up into 2 separate equations. One equation would be with the positive root 2 over 2, the other with the negative root 2 over 2. What angles make sine equal to root 2 over 2? On our unit circle, that would be pi over 4 and 3 pi over 4. And again, remember to add the 2 pi n to represent all the possible solutions. As for the negative root 2 over 2, what angles make sine negative root 2 over 2? That would be 5 pi over 4 and 7 pi over 4. So again, remember to add the 2 pi n to represent the entire family. So here we have 4 possible families for 2 theta minus pi over 2. It can either be pi over 4 plus 2 pi n, 3 pi over 4 plus 2 pi n, 5 pi over 4 plus 2 pi n, or 7 pi over 4 plus 2 pi n. Now we need to solve for theta in each family separately. Luckily, our procedure will be exactly the same for each family. First, we'll add pi over 2 to both sides. Then we can divide both sides by 2. And when we do, remember to divide each term in our family by 2. So for example, for the 3 pi over 4 plus 2 pi n, we divide the 3 pi over 4 and the 2 pi n by 2. And when we do, we get 3 pi over 8 plus pi n. And if we repeat this for the other families, we get that theta could be 5 pi over 8 plus pi n, theta equals 7 pi over 8 plus pi n, or theta could equal 9 pi over 8 plus pi n. So here we have 4 families of solutions to this equation. Oftentimes, instead of finding every possible solution to a trigonometric equation, we're only going to want solutions in a specified domain. For example, we're going to solve cosecant theta equals negative 2 when 0 is less than or equal to theta, which is less than 4 pi. Secant, cosecant, and cotangent are not necessarily the best trig functions to look at for solving equations. Oftentimes, we're going to want to rewrite them as either sine, cosine, or tangent using the reciprocal properties. Cosecant, we know, is the reciprocal of sine. Well, if 2 numbers are equal, their reciprocals are also equal. So we have that sine theta will equal negative 1/2, since the reciprocal of cosecant theta is sine theta, and the reciprocal of negative 2 is negative 1/2. Now, if we go to our unit circle, what angles cause sine to be negative 1/2? That would be 7 pi over 6 and 11 pi over 6. And remember to add the 2 pi n to represent the entire family. So right now we found all the possible solutions to our trigonometric equation. But remember, I only want the solutions from 0 to pi. So what we're going to do is we're going to plug in values for n to try to figure out specifically which solutions from each family are between 0 and 4 pi. If I make n negative, my theta would wind up being negative. Negative numbers are not going to be within 0 and 4 pi. But if I make n equal to 0, 2 pi times 0 is just 0. Anything plus 0 is itself. So I wind up with 2 solutions, 7 pi over 6 and 11 pi over 6, which do fit in my interval. Next, we'll try n equals 1. If we plug n equals 1 into our families, we get 7 pi over 6 plus 2 pi and 11 pi over 6 plus 2 pi. When we add these values together, we get 19 pi over 6 and 23 pi over 6, which are less than 4 pi. What about if I make n equals 2? Well, if I make n equals 2, 2 pi n would become 4 pi because 2 times 2 is 4. Well, I'm adding 4 pi to a value that's already positive, which means my sum would be bigger than 4 pi, which is outside of my interval. And the same thing goes if I pick n equals 3, 4, or anything larger than 1. I'm going to be adding a value to my angles that is bigger than 4 pi. So here in this restriction of 0 to 4 pi, I only have 4 solutions. And those 4 solutions are 7 pi over 6, 11 pi over 6, 19 pi over 6, and 23 pi over 6. Next, we're going to solve 2 times tangent x plus 3 equals 5 plus tangent x on the interval where x is between negative pi and pi. Unlike the previous examples, we do have 2 trigonometric expressions in our equation. Fortunately for us, they're both tangent x. So our goal is going to be to try to rewrite our equation so that way there's a single tangent x within my equation. So first, we should simplify both sides of the equation. Right-hand side, as simple as we can make it. On the left-hand side, we can distribute in 2. And when we distribute in 2, we get 2 tangent x plus 6 on our left-hand side. Now let's get all of our tangent x's to one side of the equation, and while we're at it, we can get all of our constants to the other. So we're going to subtract tangent x from both sides to get all of our tangents to the left, and we're going to subtract 6 from both sides to get our constants to the right. And when we simplify, we get tangent x equals negative 1, which is similar to the situations we've seen in past problems. Since we're dealing with tangent, which has a period of pi, we only need one solution from our unit circle. If we look to our unit circle, one solution is 3 pi over 4. So 3 pi over 4 plus pi n will be all the possible solutions to the equation. But just like in the last example, we're specifying a domain for x. We want x to be between negative pi and pi. Since I'm allowing x to potentially be negative, if I make n negative 2 or smaller, I'm subtracting an angle that is either 2 pi or larger. Well, 3 pi over 4 minus an angle that is 2 pi or larger is going to wind up being smaller than negative pi and not be in our window. So we're going to start by plugging in n equals negative 1. And when we do, we get x equals 3 pi over 4 minus pi, which becomes negative pi over 4. Negative pi over 4 is between negative pi and pi, and will be a solution. If we try n equals 0, we get x equals 3 pi over 4. This is because pi n would just be 0 when n is 0. And lastly, what would happen if we make n 1 or larger? Then we're adding an angle that's pi or larger to a positive angle. When that occurs, that's going to make our angle larger than pi itself. And we don't want angles bigger than pi. So we don't have to plug in n equals 1 or anything larger than 1 into our family. So here we only have 2 solutions, those being negative pi over 4 and 3 pi over 4. Next, we're going to find all solutions to the following equation in the interval 0 to 2 pi. In our first equation, we're going to solve 2 sine squared x plus sine x minus 1 equals 0. When we look at this problem, notice that there's only one trigonometric function, which is sine x. What makes this a little bit more difficult than our previous examples is one sine is being squared, the other sine is not being squared. So unfortunately, there's no way for me to combine those together as a single expression. But because of one sine being squared and the other is not being squared, this appears to be a quadratic-like equation that we studied back in college algebra. So to help me solve this, we're going to make a substitution. We're going to make u equal to sine theta. So anywhere I see a sine in my equation, I'm going to replace it with u. And when we do, the 2 sine squared x becomes 2u squared, sine x becomes u. So my equation becomes 2u squared plus u minus 1 equals 0. And when we consider this equation as an equation with u, this is a quadratic equation. A couple different strategies we can go about solving it. You can either use the quadratic formula or try to factor. This one can be factored, and we'll factor to 2u minus 1 times u plus 1. And if we set each factor equal to 0 and solve, we get u equals 1/2 and negative 1. But this is only the value of u. Remember, we wanted the value of theta. So using our substitution, sine theta will equal either 1/2 or sine theta will equal negative 1. And we'll solve each of these equations separately. If we look at our unit circle, when will sine theta equal 1/2? That would be at pi over 6 or 5 pi over 6. And again, remember to add the 2 pi n for the entire family. On the unit circle, when would sine theta equal negative 1? That would be when theta equals 3 pi over 2. And there would only be one such angle since there's only one point with a y-coordinate of negative 1. Now that we have all the possible solutions to our equation, we want to identify the solutions between 0 and 2 pi. If n is negative, that's going to make all of my angles negative. But if I make n positive, I'm going to be adding a value that's 2 pi or larger to already positive angles, which is going to make our angles bigger than 2 pi. So our solutions that fit within the 0 to 2 pi interval are going to occur when n equals 0. And when we make n equals 0, the only possible angles will be pi over 6, 5 pi over 6, and 3 pi over 2. Now we're going to solve 2 cosine squared 2 theta equals 5 minus 5 sine 2 theta. Unlike the last few examples that we've seen, here we see 2 trig functions, cosine and sine. When we have 2 trig functions like this, it becomes rather difficult to solve them. And one strategy is to try to rewrite our equation so that way there's only one trig function. If we look at both very carefully, notice how one trig function is squared while the other isn't. Since I see one trig function that's being squared, specifically cosine squared of 2 theta, I can apply the Pythagorean identity because that will allow me to rewrite the cosine squared as a sine squared, and all of my trig functions would just be sines. So we can replace the cosine squared 2 theta with 1 minus sine squared 2 theta via the Pythagorean identity. Now from there, let's try to simplify the equation. First, we'll distribute into 2, and then we're going to try to make this equation look like the one we just solved. Because of the square, it is looking quadratic, and we know with quadratic-like equations or even quadratic equations, we do want to make one side 0. Because I like to make the term in front of whatever's being squared positive, I'm going to move my terms on the left over to the right. So I'm going to subtract 2 and add 2 sine squared 2 theta both sides. And when we do, we get 0 equals 2 sine squared 2 theta minus 5 sine 2 theta plus 3. Now we're in a similar situation as we were in the last problem. We have a quadratic-like equation, so we can use a substitution to help simplify this equation. We're going to make u sine 2 theta, and when we substitute that in, we get 0 equals 2u squared minus 5u plus 3. You can either use the quadratic formula or factor. If we do factor, we get 0 equals 2u minus 3 times u minus 1. Now we can set each factor equal to 0 and solve for u, and we get u equals 3 halves and 1. But remember, this is only the value of u. We need the value of theta. Since u was sine 2 theta, then either sine 2 theta equals 3 halves or sine 2 theta equals 1. If we look at the first equation, sine 2 theta equals 3 halves, what angle will cause sine to equal 3 halves? Well, if we look at the unit circle carefully, all the y values of any point on the unit circle are between -1 and 1. So is it possible for sine of any angle to ever equal 3 halves? No. So the first equation has no solution. What about the sine 2 theta equals 1? If we go to the unit circle, there's only one point with a y component of 1, and that point corresponds to the angle pi over 2. So 2 theta would equal pi over 2 plus 2n pi. And if we divide everything by 2 to solve for theta, we get that theta equals pi over 4 plus n pi. But remember, we only want answers between 0 and 2 pi. Well, if I make n negative, pi over 4 minus a negative multiple pi will be negative. That's too small for the interval. If we make n equals 0, then theta will be pi over 4. If we make n equals 1, we're only adding pi, which is not that big. So theta would equal pi over 4 plus pi, which is 5 pi over 4. But if I make n 2 or larger, I'm adding an angle that's either 2 pi or larger to pi over 4. That's going to be bigger than 2 pi. So here, I only have 2 solutions within this interval, those being pi over 4 and 5 pi over 4. Next, we're going to find all solutions to secant 4x minus 3 secant squared x plus 2 equals 0 on the interval 0 to 2 pi. Now, with this problem here, we do see a trigonometric function, and I can't combine those, so I do want to use a substitution. Now, I could just use u equals secant x, but if I look very closely at the powers, I have 4 and I have 2 as my powers of secant. So instead of just making u equals secant x, we're going to make u secant squared x. Then when I make my substitution, the secant to the 4th x, which is the same as secant squared squared, becomes u squared. 3 secant squared x becomes 3u, then plus 2, which equals 0. Now I have a quadratic equation, which we can factor to u minus 1 times u minus 2, which means u is either 1 or 2. But remember, this is the value of u. I want the value of x. So secant squared x is either equal to 1 or secant squared x is equal to 2. If we square root both equations, we get that secant x equals plus or minus 1 or secant x equals plus or minus root 2. In order to make it easier to use our unit circle, instead of having our equations in terms of secant, we can rewrite it with the reciprocal identities. The reciprocal of secant is cosine. The reciprocal of positive or negative 1 is still positive or negative 1, while the reciprocal of the square root of 2 or negative square root of 2 is positive or negative square root of 2. Now, in the previous problems, when we ran into the plus or minus, we split these up into 2 equations, one for the plus or one for the minus. But we can condense this into one process. Essentially, what the first equation tells us is we're looking for angles that have an x coordinate of either 1 or negative 1. If we scan our unit circle, 0 has a x component of positive 1, while pi has an x component of negative 1. So 0 plus 2 pi n and pi plus 2 pi n would be a family of solutions to our first equation, whether we use the plus or the minus. In our second equation, we're looking for all points that have an x component of either positive root 2 over 2 or negative root 2 over 2. And from the unit circle, we get pi over 4, 5 pi over 4, 3 pi over 4, or 7 pi over 4. Pi over 4 and 7 pi over 4 calls cosine of x to be positive root 2 over 2, while 3 pi over 4 and 5 pi over 4 calls cosine x to be negative root 2 over 2. So in total, I have 6 families of solutions, but I only want the solutions between 0 and 2 pi. Well, because we're only looking at solutions between 0 and 2 pi, and we're adding 2 pi n's to each of our solutions for our families, if I make n negative, my angle will be too small. If I make n 1 or larger, my angle would be too big. So the only possible valid value I can plug in for n to make my angles fit between 0 and 2 pi is 0. Keep in mind, 0 is closed in our interval, so we will include 0 as a solution from our first family. And all of my solutions to this equation on the interval 0 to 2 pi will be 0, pi, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now we're going to find the solutions to cosine x cosine 4x plus sine x sine 4x equals the square root of 3 over 2 on the interval 0 to 2 pi. If we look at this equation very carefully, ideally, I would like to be able to simplify the left-hand side in some sort of way. In order to simplify, we really have to be familiar with our various identities that we have covered so far in this unit. If we look over our identities very carefully, there is one identity that involves us multiplying cosines, multiplying sines, and adding those results together. And that's the sum and difference formula for cosine. More specifically, the difference formula for cosine. And that is cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. So we can apply this formula to our left-hand side, and our left-hand side becomes cosine of x minus 4x, which becomes cosine of negative 3x. And since cosine is even, we can drop the negative sign inside of our input. Now we have to figure out what angles cause cosine to equal root 3 over 2. Looking at our unit circle, we get the two angles are pi over 6 and 11 pi over 6. So 3x is either pi over 6 plus 2 pi n or 11 pi over 6 plus 2 pi n. To finish solving for x, we'll divide both sides by 3. And when we divide both sides by 3, we get that our two families of solutions are pi over 18 plus 2/3 pi n and 11 pi over 18 plus 2/3 pi n. Now we're going to plug in various values of n to find all of our solutions between 0 and 2 pi. If I make n negative, 2/3 pi is bigger than pi over 18 and 11 pi over 18, so that would result in a negative angle, which is too small for our interval. So we'll start with n equals 0. When we plug in 0, anything times 0 is 0. So I'll get pi over 18 and 11 pi over 18 from my two families. When we make n equals 1, our first family will give us 13 pi over 18. Our second family will give us 23 pi over 18. And then for n equals 2, we get 25 pi over 18 and 35 pi over 18, giving us 6 solutions in total. Next, we're going to try to solve cosine of 2x equals cosine of x. And we're going to find our solutions within the interval 0 to 2 pi. What makes this equation a little bit more trickier is the inputs to the cosines are different, very similar to what we saw in the last problem. Now, in this scenario, there's a couple different ways we can resolve this issue. Ideally, I would like to be able to factor my equations when one side of my equation is 0. So we'll go ahead and we'll subtract over the cosine x. Now I'm in a situation where I'm subtracting cosines, but since one side is 0, I would like to have my other side factor to use the zero factor principle. This is an ideal situation for the sum to product identity. More specifically, we'll use the one that involves subtracting cosines. And the identity states that cosine of alpha minus cosine of beta equals negative 2 sine of alpha plus beta over 2, sine of alpha minus beta over 2. Applying the identity to our left-hand side, we have that negative 2 sine of 2x plus x over 2 times sine of 2x minus x over 2 equals 0. Because negative 2 is not 0, we can go ahead and divide both sides by negative 2 and simplify what's inside of our sine functions. And we have sine of 1/3 x times sine of 1/2 x equals 0. From there, we can use the zero factor principle, set each of our sine functions equal to 0. And fortunately for us, since both sine functions equal 0, we're just looking for angles that make sine 0. And the only angles that make sine equal to 0 are 0 and pi. So we have 3/2 x equals 0 plus 2 pi n, 3/2 x equals pi plus 2 pi n, x over 2 equals 0 plus 2 pi n, or x over 2 equals pi plus 2 pi n. To solve the first two equations with the 3/2 x, we'll multiply both sides of the two equations by 2/3. And when we do, we get x equals 0 plus 4/3 pi n, or x equals 2/3 pi plus 4/3 pi n. For the second set of equations, we just need to multiply both sides by 2. We get x equals 0 plus 4 pi n, and x equals 2 pi plus 4 pi n. Now from there, we would have to figure out what our solutions are specifically between the interval 0 and 2 pi. Clearly, n cannot be negative. Otherwise, in all four families, we'll wind up with negative solutions, which are outside of our interval. If we make n equals 0, our first family will give us 0. Our second family will give us 2/3 pi. Our third family will give us 0. But we already have 0 listed. We don't need to list it again. And our last family would give us 2 pi. But our interval is open at 2 pi with the parenthesis, which means 2 pi shouldn't be included. So our third and fourth family for n equals 0 do not provide us with any new solutions. Now for n equals 1, our first family will give us 4/3 pi. Our second family would give us 6/3 pi, which is the same as 2 pi. But remember, 2 pi is not included in our interval, so 2 pi is not included as a solution. As for our third and fourth family, I'm going to get 4 pi and 6 pi respectively. That is too big for our interval, so no new solutions will be produced from our third or fourth family. As for n equals 2 or higher, the 4/3 pi n and the 4 pi n would be too big of values to add. So here in total, we're left with 3 solutions: 0, 2 pi over 3, and 4 pi over 3. Next, we're going to try to solve the following equation on the interval 0 to 2 pi. And we have cotangent of x plus cosecant of x equals 1. With this kind of equation, we have cotangent and cosecant, which we don't necessarily like working with, so we'll rewrite them in terms of sine and cosine. Cotangent of x equals cosine of x over sine x, while cosecant x equals 1 over sine x. From there, we can clear the denominators by multiplying both sides by sine x. On the left-hand side, when we distribute in the sine x, we get cosine x plus 1, and on the right-hand side, we get sine x. Now from there, let's get all of our trig functions to one side and the 1 to the other side. 1 and sine x from both sides, and we get that cosine x minus sine x equals -1. Now we'll try to make our difference into a product. If we look back at our sum and difference formulas, we don't have a property for the difference of cosine and sine. However, we can use the cofunction identities to rewrite the cosine or the sine into the other trig function. So we could write sine x as cosine of pi over 2 minus x. So thanks to the cofunction identities, I'm now subtracting 2 cosines, and I can use my fourth sum to product formula. And we get -2 sine of x plus pi over 2 minus x all over 2 times sine of x minus pi over 2 minus x all over 2 equals -1. If we simplify what's inside of our sines, and we get -2 sine pi over 4 times sine of x minus pi over 4, which still equals -1. Pi over 4 is an angle we know on the unit circle, so we can evaluate. The 2's cancel. We can divide both sides by -√2, and we get that sine of x minus pi over 4 equals √2 over 2. So if we use our unit circle, we get that sine is √2 over 2 for the angles pi over 4 and 3 pi over 4. So by adding the pi over 4 over, we get x equals pi over 2 plus 2 pi n, and x equals pi plus 2 pi n. However, we can actually rule out one of these families. And this is where we have to be careful by multiplying both sides of an equation by an expression when clearing denominators. If we look at our original trig functions that were in our equation, cotangent and cosecant both can be undefined, specifically at angles where the y component is 0. And that's because cotangent is x over y, while cosecant is 1 over y. Well, what angles have a y component of 0? Those are ones coterminal to either 0 or pi radians. So the family x equals pi over 2 plus 2 pi n, can that be a solution to my equation when written in terms of cotangent and cosecant? No, because the y component of the points associated with angles coterminal to pi will be 0, causing both cotangent and cosecant to be undefined. On the other hand, pi over 2 is safe to plug into cotangent and cosecant since their y components are 1. Now we can figure out our solution specifically between 0 and 2 pi. N cannot be negative. If n is 0, you get pi over 2. But if n is 1 or larger, we're adding 2 pi, which is too big. Anytime you're dealing with equations involving cotangent, tangent, cosecant, and secant mixed together, where we had to clear the denominators to write them in terms of sine and cosine, it's always a good idea to check your solutions to make sure you don't have any extraneous families of solutions. Next, we're going to solve cosecant x equals secant x. Similar to before, we do want to try to work in terms of sine and cosine, and luckily cosecant is the reciprocal of sine, while secant is the reciprocal of cosine. So since we have cosecant x equal to secant x, that's also going to tell us that their reciprocals, sine x and cosine x, are also equal. From here, we do want to try to simplify to one trig function. Now, we already know because of the secant x, I can't plug anything into secant x that corresponds to an angle with an x component of 0. That's because that'll lead to 1 over 0, that'll be undefined. That's equivalent to saying that cosine x cannot be 0. So one option we could take is we could follow the method we did in the last problem, subtract over the cosine x, use the cofunction identities and the sum of the product identities, or because we know cosine x cannot be 0, we can divide both sides by cosine x without risk of missing solutions. In general, it's not best practice to divide by expressions, but it's okay as long as we know those expressions cannot be 0. Since secant x is in my equation, then I know by the definition of secant x, cosine x cannot be 0 at the same time, and have secant x be defined. My left-hand side becomes tangent x. My right-hand side is 1. So now we need to solve the equation tangent x equals 1. Going to our unit circle, we know one angle is pi over 4, and since tangent has a period of pi, we're adding pi n. Now we can plug in values for n to determine all the solutions between 0 and 2 pi. If n is negative, our angle will be too small. If we plug in 0, we get pi over 4. If we plug in 1 for n, we get 5 pi over 4. If we plug in 2 or more, we are outside of the interval. So we only have two solutions, pi over 4 and 5 pi over 4. Now we're going to talk about how to approximate the solutions to trigonometric equations. If we take a look at the equation 3 sine x plus 5 equals 4, just like with any other problem that we've done before, we do want to start by isolating sine x if we can. So here we would subtract 5, divide both sides by 3, and we get sine x equals -1/3. The problem is -1/3 we do not see as a y value for any point on the unit circle. When situations like this arise, we need to try to approximate a solution to this equation. The problem is we have to be very careful how we approximate. From what we've discussed so far about trig functions, most of the time, sine and cosine have two families of solutions. Because sine is negative, that means our angle x must be in quadrants 3 or 4. To help us figure out what our solutions are, we're going to use reference angles. Our solutions to our equation sine x equals -1/3 x are going to have the same reference angle. So if I can figure out what this reference angle is, I can use geometry to help me figure out families of solutions. To help me solve this, I want to find the reference angle to x. If we call our reference angle x prime, we know from our discussions from reference angles that sine of our reference angle would equal 1/3, since the way we would figure out the trig functions with reference angles is we would evaluate a trig function at the reference angle and then throw a positive or negative value in front of it depending on the quadrant the original angle was from. Since the reference angle is always acute, meaning it's between 0 and pi over 2 radians, that means our reference angle equals sine inverse of 1/3. If we go into Desmos, we get that sine inverse of 1/3 is approximately 0.34. Now we can figure out an angle in each quadrant. In quadrant 3, we know the top half of our plane is pi radians. The pi plus our reference angle would equal our angle in the third quadrant. So one family of solutions would be our reference angle plus pi, and because we want the family, plus 2 pi n. As for our second family, our solution in the fourth quadrant plus our reference angle makes a full rotation. In other words, if we take away our reference angle from 2 pi, that would be our solution in the fourth quadrant. And we'll add 2 pi n for the entire family. If we simplify and approximate the 0.34 plus pi and the 2 pi minus 0.34, we get 3.48 plus 2 pi n and 5.94 plus 2 pi n as our two families of solutions. If we plug in our values of n, anything negative or positive will make our angle too small or too big. So the only n value that will work is 0, and our solutions are approximately 3.48 and 5.94. Next, we're going to try to solve 3 tangent squared x equals 7 secant x minus 7. In this problem, there's a couple different ways we can solve this problem. Usually when we solve the secant, we did try to rewrite them. But here, we're going to keep the secant x because I see that tangent squared x. And I know tangent and secant are related with the Pythagorean identity. Specifically, I know that 1 plus tangent squared x equals secant squared x. So I can rewrite that tangent in terms of secant and then try to use a substitution to help me solve later. And I get tangent squared x equals secant squared x minus 1. So I'll rewrite the left-hand side as 3 times secant squared x minus 1. And now we're in a similar situation as we were a few problems ago. Just instead of sines and cosines, we have secants. Distribute into 3. And since this is looking quadratic, we'll get all of our terms to one side. And we get 3 secant squared x minus 7 secant x plus 4 equals 0. Now we can make our substitution. We can make u secant x. And upon substitution, we get 3u squared minus 7u plus 4 equals 0. And we get 3u minus 4 times u minus 1 equals 0, which means u is either 4/3 or 1. But remember, these are the values of u. We need the values of x. So from this, we either have that secant x equals 1 or secant x equals 4/3. Now we can go ahead and rewrite everything in terms of sine or cosine. Thanks to the reciprocal properties, secant, we know its reciprocal is cosine, and the reciprocal of 1 is 1. And the reciprocal of 4/3 is 3/4. 1 is a value that we can see as an x component on the unit circle. Cosine of x will equal 1 on the unit circle at the angle 0. So one family of solutions is 0 plus 2 pi n, which we don't have to use the inverse trig functions to help us. As for the cosine x of 3/4, 3/4 is not an x value we see on the unit circle for any points. So that's when we're going to need to use the inverse trig functions to help us. Since 3/4 is positive, that tells us we need to find angles that make cosine positive. Those would be angles in quadrant 1 and quadrant 4. If we let x prime be our reference angle, then cosine of our reference angle would equal 3/4, where we just ignore the sign. So x prime equals cosine inverse of 3/4, which is approximately 0.72 radians. Now we can form our two families of solutions for cosine x equals 3/4. In quadrant 1, our reference angle will equal x. So one family of solutions would be 0.72 plus 2 pi n. As for the other family, since our other angle is in quadrant 4, then just like before, we'll find our angle by doing 2 pi minus 0.72, since the reference angle and our solution in the fourth quadrant make one full rotation. So our family of solutions in the first quadrant will be 0.72 plus 2 pi n, while in the fourth quadrant, we get 5.56 plus 2 pi n. Now we'll plug in values of n to find our solution. The only values of n that will work are going to be n equals 0, negative, and positive values of n are going to make our angles too small or too big. So after plugging in n equals 0, we get that the only three solutions to the equation between 0 and 2 pi are 0, 0.72, and 5.56.